Hey everyone, and welcome back to another Explainer. Today, we're tearing down a really fascinating coding challenge from July 2026. Specifically, we're diving into a post by Ang from Notes on Haskell Programming, part 189 to be exact. We're going to look at a real-world code makeover, taking a bulky, kind of clunky function and slimming it way down into this incredibly elegant data-driven solution. Okay, let's jump right in.
Section 1. The Number Conversion Challenge. Converting Gregorian years to Chinese text.
Okay, let's dive into this. This is the exact programming problem Ang was tackling. It's a classic localization hurdle, really. We want to take a Gregorian year integer, say 2026, and transform it into a Chinese numeral text string. At first glance, it seems super straightforward, right? Just a simple one-for-one character swap. But before we look at the baseline code, I want you to put on your programmer's hat for just a second. How would you actually architect this conversion? If your boss handed you this exact requirement right now, what's your first move? Would you reach for an array? Maybe wire up a giant if-else statement? Just think about what your initial instinct is. Section 2. The pattern matching approach. The straightforward baseline. So let's start by looking at Ang's original approach. We have a vertical list of pattern matching in Haskell. We've got a function called digit to Chinese mapped out individually, line by line. 0 equals the Chinese character for 0, 1 equals 1, and it just continues sequentially all the way down to 9 equals 9. And honestly, as Ang notes, this method is incredibly straightforward. It gets the job done, it's highly readable, and you literally do not have to guess what this code is doing. But what happens if the character passed in isn't actually a number? Well, that is where the fallback logic comes in. You can see it right here with digit to Chinese, C to C. This simple catch-all just sits at the very bottom of the pattern matching list. It basically means any non-numeric character, a dash, a letter, a space, it just passes right through completely unchanged, which of course prevents the whole thing from crashing. Section 3. The data-driven refactor, shrinking the code footprint. Now this is where things get really fun. This brilliantly illustrates the core makeover. We've gone from 11 entire lines of kind of repetitive vertical pattern matching down to just 3 incredibly sleek, compact lines of logic. This new version builds a mapping table using 3 things, from maybe, lookup, and zip. We've essentially taken hard-coded algorithmic logic and compressed it down into dense, concise data. It's a real game changer. Let's break down the mechanics of how this actually works. The real magic here relies on the Haskell's zip function. Imagine taking an input string of digits, 0 through 9, and an output string of those Chinese numerals. Zip takes them and, just like a zipper on a jacket, perfectly pairs them together index by index. It essentially constructs a dictionary-like data structure right on the fly, locking each standard digit firmly to its corresponding Chinese character. Okay, but we still need to handle our fallback logic, right? We can't just forget about the non-numbers. That is where from maybe steps up. To put it simply, from maybe is a Haskell function that takes a default value and a maybe value. If the maybe is nothing, it just returns your default. So, if our lookup function searches our newly zipped map for a random letter, say an A, it obviously won't find it. It returns nothing. Then from maybe steps in and cleanly returns the A itself. It is a super elegant way to handle that exact same catch-all fallback logic we saw in the old code. It's just done in line. Section 4. Weighing the trade-offs. Readability versus extensibility. So what does this all mean? Why bother doing this refactor at all? Well, while the original pattern matching was arguably more straightforward for beginners to read, some people do find Ziv a bit dense, the real massive benefit here lies in software architecture. As Ang points out, quote, however, when it comes to extensibility, then we simply just declare a map and swap it into the lookup function. So the crucial point is that by turning your hard-coded logic into flexible data, you completely decouple the mechanism from the mapping itself. The lookup function literally doesn't care what data it's searching through, just as long as it gets a valid map. Let's move to and see how this builds into massive real-world applications. What if the business requirements suddenly change? Let's say your app now needs to support traditional Chinese numerals, or formal numerals, or even financial numerals, which are specifically designed to prevent fraud. With that old method, you would be writing a brand new 11-line function for every single one of those. But with this data-driven approach, it requires absolutely 0 changes to your core function logic. You simply just declare a new map, plug it in, and you're good to go. Which brings us to a really important takeaway for all of us. Where are you choosing rigidity over extensibility in your own code? It's so incredibly easy to just hard code a solution because, well, it's fast in the moment.
But take a fresh look at your code bases. Are there places right now where swapping to data-driven lookups could save you massive refactoring headaches down the road? Definitely something to chew on. Thanks so much for joining me for this explainer, and keep building smarter, more flexible structures.